the afternoon is Francis Bischoff from the University of Oxford. He will be talking about Brane quantization of Toric Poisson varieties. And I apologize that we have at the end of the talk 10 minutes more. Okay, you hear me?
Mm-hmm. Okay, thanks. So yeah, thanks to the organizers for giving me this opportunity to speak and also for putting together this great conference. Second. Okay, so this is work that's joined with Marco Gualtieri, and we actually put a preprint on the archive last week about this. And this work, it's part of an ongoing project where we're trying to use generalized complex geometry to give a geometric basis for non-commutative algebraic geometry. And in this talk, I'll be discussing how this applies to non-commutative projective geometry and deformation quantization. So to start, I just want to start with the motivation, the geometric quantization of Kähler manifolds. So let's start with just a compact symplectic manifold and go over the geometric quantization. So the first thing that we need is a prequantization, so a unitary line bundle L with a connection nabla whose curvature recovers omega. And then next, we choose a polarization, so a way of kind of splitting the coordinates on M to position and momenta. So we'll choose a complex polarization. So that's defined to be a complex structure I, which satisfies these two things. So the first equation, this says that the symplectic form now has type 1, which means that the subspace, for example, of 0, 1 vectors is a Lagrangian. And then the second condition, which is not strictly necessary, this says that I and omega defines a metric, so it's positive definite. Okay, so then given the structure, we can define the quantization. So the quantization is supposed to be the space of polarized sections. So what we're supposed to do, we take the curvature, the connection nabla, and we take its 0, 1 component, and we take the sections that are killed under this. So in other words, we're taking the global holomorphic sections of L, and this defines the quantization. Okay, so in the geometric quantization of omega, the complex polarization, it plays an auxiliary role. And in many interesting examples, the quantization does not actually depend on the choice of I. So we have some type of independence of polarization results. So if we want to see where the complex structure comes in, what we need to do is quantize not just omega, but the entire kind of scaling family, omega, 2 omega, 3 omega, and so on. And if we put all of these quantizations together, then what we get is the homogeneous coordinate ring, which I've written here as A. And by the Kodaro embedding theorem, which says that this algebra defines an embedding of M with its complex structure into a projective space. So what this tells us is that the algebra, the kind of the product on A, that's what encodes the polarization I. Okay, so if we kind of believe that we have an independence of polarization, then what we can do is if we deform the polarization, then the underlying vector space will remain unchanged. But the product on the algebra, that will get deformed. Okay, so one type of deformation is just if we deform the complex structure, and infinitesimally this is controlled by this cohomology group. And the deformations of the product that would result, they would kind of correspond to the different ways of endowing M with the structure of a projective variety. But in fact, there's kind of a larger space of deformations of the complex structure. It's actually the deformations of the complex structure itself. It's only one piece in a larger space. And this larger space of deformations, this corresponds to the deformations of I as a generalized complex structure. So I'll get back to this in a moment. And what I'm going to be interested in for this talk are the deformations arising from this part. So these are the deformations which are given by holomorphic Poisson brackets. And the expectation is that if we deform the polarization in this direction, then just as before, the underlying vector space, it might stay the same, but the product will deform, but now to something non-commutative. Okay, so let me start by now just explaining generalized complex geometry. So a generalized complex structure, it's a complex structure on the tangent plus the cotangent bundle. So it's an endomorphism I of t plus t star, which squares to -1. And it has to satisfy an integrability condition with respect to the natural bracket on the sections of the space, which is called the Courant bracket. This is a bracket which extends the Lie bracket of vector fields. So if we have a complex structure, that gives an example of a generalized complex structure. So in this notation of a block matrix, I'm kind of imagining I have Tm here, T star M here, and then T and T star. So the way that we get the generalized complex structure from the complex structure is we combine I, which goes from Tm to Tm, and I star, which goes from T star of M to T star of M. Okay. So here's another example. This is kind of at the opposite extreme, which is at a symplectic structure. So this gives another example of a generalized complex structure. So you can think that generalized complex geometry, it's some type of geometric framework which unifies both complex and symplectic geometry. But it also includes holomorphic Poisson geometry. And these can be viewed as giving deformations of a complex structure. So just to review, a holomorphic Poisson structure, it's a bivector on the manifold, which is first of all holomorphic, and it satisfies an integrability condition. So here I've written it as the Schouten bracket of the bivector with itself is 0. This corresponds to a Jacobi identity. Okay, and this is a holomorphic Poisson structure, but we can decompose it into real and imaginary parts. So P and Q, these are real Poisson structures. And what we can do now is put Q in the top hand corner, and this will define a generalized complex structure. And if you look at this example, when we set H bar equals to 0, we just recover the complex, the GC structure of a complex structure from this last slide. But when H bar is non-zero, we get a genuinely new generalized complex structure. Okay, so now in order to see how we can deform the homogeneous coordinate ring, I want to now recast it in terms of the category of coherent sheaves on the complex manifold. So this first equality is just the definition that I put up earlier, but now I want to view it as something happening in the category of coherent sheaves. I want to view it, these individual pieces, as homomorphisms from O to phi to the n of O. So here O is just the trivial line bundle, and phi here is an autoequivalence of the category of coherent sheaves, which is given by taking a sheaf and tensoring it with the line bundle L. So as a result, this phi to the n applies to O, that's L to the nth tensor power. So what we have here is homomorphisms from O to L to the n. So this gives us the homogeneous coordinate ring, and in this formulation, the product on the algebra is given by composition of homomorphisms, but where we have to use this autoequivalence to kind of shift the domain of a map. So it's like something like f composed with g is some phi to some power of k applied to f composed with g. Okay, so if we want to deform A now, this in the direction of this Poisson structure, what this says is that we should deform the category of coherent sheaves and this trivial line bundle and this autoequivalence. Okay, so I'm going to start with what to do about the category. So a generalized complex structure is conjectured to have a category of boundary conditions. And the objects of this category are called branes. And in the two extreme cases of complex structure and symplectic structure, these things are well known. So when you have a complex structure, the category of boundary conditions is called the B model, or coherent sheaves, and the objects are things like vector bundles and coherent sheaves. When we have a symplectic structure, the category is the A model, or the chi category, where the objects are given by Lagrangians with some extra structure on them, or more general coisotropic branes. So these were described by Kapustin and Orlov. Okay, so what about branes for the GC structure associated to a holomorphic Poisson structure? So here's a definition, which it's not the most general definition of a brane, but it's going to be good enough for my purposes. So a brane on this GC manifold, it's defined to be a unitary line bundle with connection, L nabla, such that the curvature F, it satisfies this following equation. And so there's a few things to notice about this equation. The first thing is that if the Poisson structure is 0, then this term here goes away. And so what we're left with in this case is the equation that specifies that the form here is of type 1,1. And so in this case, we recover the usual definition of a holomorphic line bundle with connection. In this case, nabla would be the Chern connection. The second thing to notice is that we always have a solution which is given by f equals to 0. So what that means is that we always have a canonical brane on a holomorphic Poisson manifold, which is given by the trivial bundle with a trivial flat connection. Okay, so far, this is telling us how do we deform the category of coherent sheaves. We're deforming it to this category of boundary conditions for this GC structure. The trivial bundle, it deforms to this canonical brane. And then the last thing is the autoequivalence. So this is a theorem of Gualtieri, provides us with this. So the setting is we're starting with a holomorphic prequantization of a Kähler manifold. Then the theorem says that if L admits a Poisson module structure, then this functor of tensoring with L, it deforms to an autoequivalence T of the category of boundary conditions. And here, a Poisson module structure, this is a linear Poisson structure on the total space of L, which reduces to sigma. Okay, so let me now just summarize what we have so far and explain how this gives rise to a deformed homogeneous coordinate ring. So we're starting with a pre-quantized Kähler manifold. We equip it with a holomorphic Poisson structure. So this gives a deformation of the complex structure to a generalized complex structure. The trivial bundle, it deforms to a brane for this category of boundary conditions. And then given the structure of a Poisson module on L, then the functor of tensoring with L, it deforms to an autoequivalence of the category. So now what we can do is we can take this autoequivalence T and we can apply it to this brane B0, and that will allow us to define new branes. So we obtain a sequence of branes by successively applying T to this trivial brane here. Okay, so this gives us all the ingredients that we were using before to define the homogeneous coordinate ring. So we can define now a deformed homogeneous coordinate ring in this way. We're taking the homomorphisms from this brane B0 to a brane Bn. And the composition now is given by the composition of morphisms, where again, we're using the autoequivalence T to kind of match the domain of a morphism. Okay, so there's a problem with this approach, which is that so far, the morphisms in the category of boundary conditions, they have not been defined. So this kind of approach, so far, it doesn't really work. So, so what I want to do in the rest of the talk is I want to discuss a proposal for how to actually implement this construction. And this is based on making use of an A model of an associated symplectic manifold. So to start, I want to explain how this works in the case of geometric quantization of a Kähler manifold. So going back to this example. So the main idea here, and this is actually something that goes back to Donaldson's work, although it wasn't phrased in this way, but the idea here is to encode the Kähler manifold as a pair of A branes in the cotangent bundle of the manifold. So here are the two branes. The first is a Lagrangian brane, which is given by the zero section with a trivial flat connection. And the second brane is a so-called space-filling brane. So these are these more general branes of Poisson and Orlov. And this thing, it's basically supported on the entire cotangent bundle. That's why it's called space-filling. And the data that specifies it is a unitary line bundle with connection. And this is obtained essentially by pulling back this prequantum line bundle from the base to the total space of the cotangent bundle, but then correcting the connection by adding the real part of this one form alpha naught. So alpha naught here is the canonical primitive of the canonical holomorphic symplectic form on the cotangent bundle. Okay, so why does this define a brane? So let me recall the definition. So a unitary line bundle with connection is a space-filling brane if when we take its curvature f, so this is the curvature of the connection, and we add it to I times the symplectic form, then this gives a holomorphic symplectic form. So if we look in this case here, so f being the curvature of this connection nabla hat, then if we add it to I times omega naught, then what this gives is omega naught, the holomorphic symplectic form, plus the pullback of the Kähler form. So this gives the twisted cotangent bundle, which is a holomorphic symplectic manifold. Okay, and these two branes, they really do encode the Kähler geometry. We can actually recover the Kähler structure by taking these two branes and kind of intersecting them in this way. Okay, so here's a picture. So we have the cotangent bundle mapping down to M. We have in purple here this zero section, which is a Lagrangian brane, and then supported on the entire space, this space-filling brane B, which is the unitary line bundle with connection. Okay, so what about quantization? So as it turns out, this way of encoding a Kähler structure, it fits in perfectly with a proposal for quantization, which is developed by Gualtieri and Witten. And so what this suggests as a definition for the quantization is to take it to be the space of homomorphisms between this Lagrangian brane L and the space-filling brane B. So that's what we're going to take to be the quantization. So this B, it's not a Lagrangian brane, it's a coisotropic brane, and these are not well understood. So in general, such a space of homomorphisms is difficult to compute. For the types of calculations that I'm going to have to do in practice, we have a proposal that does the job. And this proposal is based on geometric quantization. And so it works as follows. It's basically 3 steps. So first, we equip this space-filling brane B with a holomorphic prequantization. This is given by, it's the same line bundle, the pullback of L. And we're taking almost the same connection, but we're adding, instead of just the real part of alpha naught, we're adding alpha naught. And now this thing, it will actually now define a holomorphic line bundle with a holomorphic connection that prequantizes the holomorphic symplectic form. Okay, then the next step is we want to choose a holomorphic polarization, so a foliation by holomorphic Lagrangian submanifolds. And in this case, we can take it to be given by the fibers of the projection map. So here I've drawn them in these black vertical lines. This gives us the foliation. Okay, and then the definition of the homomorphisms, we define it to be the space of holomorphic D-flat sections, which are along the leaves of the polarization that intersect L. So if we look back at this picture, all of these vertical leaves, they intersect L, and being D-flat along these vertical directions, that's telling us that the sections of U are pulled back from the base. So we can see that we recover in this way the global holomorphic sections of L. So later on, I'm going to consider a different polarization, and this kind of isomorphism is going to be a bit more non-trivial in that case. But that's how we can get the geometric quantization from this perspective. Okay, so what about the homogeneous coordinate ring now? So for the homogeneous coordinate ring, this relies on another structure on the cotangent bundle. The cotangent bundle isn't just a symplectic manifold, it's a vector space. So we can add points in a fiber. So in fact, what this gives is the structure of a symplectic groupoid on the cotangent bundle. And what this means is that it endows the A model with the structure of a tensor product. We can tensor branes together. So let's look at what happens when we tensor our 2 branes, L and B. So remember, L was the 0 section. The 0 vectors are the unit for the addition. And so this 0 section is going to be the monoidal unit for the tensor product. In particular, if we tensor it with itself, we just get back L. On the other hand, if we take the tensor product of B with itself, then what we're going to get are the integer rescalings of the Kähler form. So what this means then is that we can write now the homogeneous coordinate ring as follows, as homomorphisms from this Lagrangian brane L to the different tensor powers of B. And now the product on this algebra is going to be induced by the tensor product of branes. Okay, so this is how we can get the homogeneous coordinate ring from the A model approach. And this, we expect it to generalize to the setting of generalized complex geometry. So I'm just going to sketch this. So first of all, a generalized complex structure, it always has an underlying real Poisson structure, which I'm calling Q. And there is this real Poisson structure, it can always be integrated to a symplectic groupoid, at least a local symplectic groupoid. So we can think of this thing, the symplectic groupoid, as a space of Hamiltonian paths on the manifold up to Hamiltonian homotopies. So it's something that's like the fundamental groupoid of a manifold, but it's adapted to the Poisson structure. And so this thing, G omega, it's a symplectic manifold, but it also has this product, which corresponds to concatenating paths. And so what this means is that we get an A model, and it has a tensor product structure. And the unit object here is given by the identity bisection. This corresponds to all of the constant paths that just lie at a single point. Okay, so all of the structure here, this comes from just the Poisson structure. There's more to a generalized complex structure. So we get a bit more structure. So what we can do is given a point in G, which we think of as a path in M, we can map it to its starting point, its source, and its endpoint or target M. So we get this map, T times S, going from G to M cross M. And because this thing is symplectic, and this thing we can equip it with the product of the generalized complex structures, really this is a map between two generalized complex manifolds, two generalized complex structures. And this map here, it can be equipped with the structure of a generalized holomorphic map. And so what this means is that if we have GC branes on I, say BI and BJ, then what we can do is we can take their product to get a brane inside of M cross M. And then we can use this map, which is generalized holomorphic, to pull them back. And that produces an A brane in the groupoid, which I'm calling Bij. So you can think of this brane Bij, this is paths in M which go from Bj to Bi. Okay, and then we can use this to define the space of homomorphisms from the branes Bj to Bi. We take it to be the space of homomorphisms in the A model from this identity bisection to this brane Bij. Okay, so this is a proposal for how to, the other thing is that the composition of morphisms, this will be induced by the tensor product. Okay, so the upshot is that this gives a proposal for how to compute a category of boundary conditions. How do we calculate the homomorphisms between branes? And so as a result of this, we can apply it to the example where we're trying to get this deformed homogeneous coordinate ring. In practice, this is a bit difficult to implement because, as I said, so this Bij, it's in general a coisotropic. It's a coisotropic brane, and these things are not well understood. So, in practice, this is still not obvious how to compute this. So, what I want to do in the remaining time of my talk is to sketch an implementation, which we do in the paper. We implement this construction in the case where we have a toric Poisson structure. So that's what I'm going to do for the remainder of the talk. So yeah, so let's go to the setting. We're starting with a toric Kähler structure. So here's the Kähler structure. It's equipped with a Hamiltonian action of a compact torus, which extends to a holomorphic action of its complexification. This holomorphic action, it will lift to a Hamiltonian action on the holomorphic cotangent bundle with a moment map, which I'm denoting J naught. Now let's take an equivariant prequantization of the Kähler structure. So first of all, we have the prequantization L nabla, and we take a lift of the action of the complex torus to an action by linear automorphisms of L. Okay, so In order to deform the homogeneous coordinate ring of the scalar structure, we need a holomorphic Poisson structure. And we're going to specify this using an R matrix. So this is going to be, you can think of this just as an anti-symmetric n by n matrix. This really, you can think of it as the Lie algebra of the torus. And so given this R matrix, we can use the torus action to push it forward to get a bivector on the manifold. And this will be a holomorphic Poisson structure. And then using this lift rho hat, we can push it forward also to get the structure of a Poisson module on L. Okay, so these are all the ingredients that we need now to get the homogeneous coordinate ring. Okay, so first, what is the symplectic groupoid of this thing? So it turns out in this case that the symplectic groupoid is a deformation of the cotangent bundle. So the underlying symplectic manifold is unchanged. It's still the cotangent bundle, but the structure maps gets deformed. And here, let me give a picture. So before we had the groupoid given by the cotangent bundle. So the paths, they basically don't move around on the manifold, or they have to stay in a single point. And so the starting point and the end point of a path, they both coincide, and it's given by this projection map. But when we turn on the Poisson structure, everything gets deformed. So these now split, the target and the source maps are different, and we get kind of a different multiplication structure. And if you just look at the formulas, you can see that it's involving both this R matrix C and this Hamiltonian J0. Okay, so the result of this is that since the symplectic manifold is unchanged, its A model, the underlying category, will be unchanged, but the tensor product structure is going to get deformed. Okay, so this is the category where we're going to implement our construction. Now we need some branes. So first of all, we have this identity bisection. So this is still given by the zero section. So this is a Lagrangian brane. And now for the second brane, this space filling brane, remember we had the way that we were supposed to produce a brane on the groupoid is we're supposed to take two branes on the GC manifold, on the underlying holomorphic Poisson manifold. So we take this B0, which is given by the trivial bundle, and we take this B1, which is obtained by applying our autoequivalence to B0. And then we pull it back by this target and source map to get an A brane on the cotangent bundle. And it turns out in this case that the space filling brane that we're going to get in this construction is going to be exactly the same as the one that we had in the Kähler case. So that's going to be unchanged. And so what that means is that the space of homomorphisms between them, it's going to be it's going to give us basically the same answer as before. These branes are unchanged. I want to, however, give a slightly different construction because it will be useful we need to choose a different polarization. So this will be important for the tensor product structure. So instead of just choosing the vertical polarization given by the fibers of the projection map, which is no longer available to us, I want to choose a polarization which is given by the fibers of a holomorphic moment map. So here's a picture of what's going on. So remember the definition for the space of homomorphisms from L to B is we're supposed to take the D flat sections along the fibers of J, which intersect this Lagrangian L. But now this is going to behave a lot differently than in the case of the projection. So there's two things that are going to be different. The first thing is that not all fibers of J admit global flat sections. So we get a quantization condition. The fibers of J which admit flat sections, those correspond to the integer points in C to the n. And I've tried to indicate them here with these red dots. The second thing, which is different, is now that the fibers of this map, they don't all intersect L. We're only supposed to take the fibers that intersect L. And the only fibers that intersect L, they correspond to the points which lie inside of this polytope, which turns out to be the Dalzand polytope of the toric variety. So the result is when we're computing the homomorphisms from L to B, we're only supposed to take these lattice points in the Dalzand polytope. So when we do this, we again get the isomorphism between the space of homomorphisms and the global holomorphic sections of L. Okay, so just one final thing. So if we want to get the deformed homogeneous coordinate ring, what we're going to do now is we're going to take the tensor powers of the brane, and we're going to take the homomorphisms from L to these tensor powers. And then the product is going to be defined by the tensor product. But now it's given by the deformed tensor product. So I can't really go into detail in how this works, but just to indicate one thing, the tensor product on the brane is going to be encoded by a cocycle. And here's a formula for a cocycle. This is telling us how to tensor together two sections of this line bundle. And you can see it involves this moment map J and also this R matrix C. Okay, so we do this in detail in the paper, and here's a theorem that we get, which is that when we implement this procedure, that what we get is an algebra, and the underlying vector space coincides with a homogeneous coordinate ring, but the product has been deformed in this way. Okay, so I'm going to end here. Thanks.
Yep. Thank you very much for your talk. Are there questions?
Hello, can you hear me? Thank you very much for your talk. It was really interesting. I was wondering if you could say something about the generalized complex structure that you create from the Poisson structure. In particular, I was wondering why you seem to treat preferentially the imaginary part of the Poisson structure, and why the poor real parts seem to be a little bit neglected.
Yeah, so that's a good point. But I guess the fact is that P is it's related to Q with the complex structure, right? Because it's holomorphic. So the real and the imaginary part are not really independent.
I see. All right, that's makes a lot of sense. Yeah.
So maybe here I'm kind of tacitly assuming that this deformation parameter is real, but it makes sense to take to be complex. And if we took it to be complex, the thing coming in here, it would not really be Q, it would be a combination of Q and P.
I see. And a combination to make specifically that number real.
Yeah, like we would take H bar times C, and then we would want to take the imaginary part of this thing. And that if H is not real, it would not be Q anymore. It would be a combination of the Q and the P.
Right, that makes sense. Thank you very much.
Further question?
Yeah, maybe I could ask a question here online. So I think it was something you didn't really use in your talk, but you said it in the beginning, and it is certainly the mantra in this area quite a lot. You said that the quantization is independent of the polarization, and it's really such just an auxiliary choice. And I just wanted to remark that, well, there are a few examples where we indeed know this. But beyond those few examples, I don't really think there is a lot of evidence that the quantization is independent of the polarization.
Mm.
And in fact, I think that it should in some very interesting way depend on the polarization. But in some sense, it's transverse to your discussion, because you are discussing deforming into a generalized complex structure direction, and not really deforming I along the H1 directions of the T.
Yeah.
But I just wanted to make this remark, and I will comment on this quite a lot in my own talk.
Yeah, that's a good point. That's why I put many, and it
Okay.
was somehow just meant for motivation.
Yeah.
Yeah, thanks for the comment.
Are there further questions from out there? I'm delighted. Okay.
By the way, maybe I can supplement with another question, which is more aimed at your talk. Can you compute some examples, say, projective spaces or something like this, where you can explicitly compute what your projection gives?
Yeah, so we do it for all compact toric varieties with the torus invariant Poisson structure.
Yes, but so maybe you can show me the product structure again then.
Mm-hmm. So yeah, it's essentially we take the sections of the line bundle and we just tensor them, but then we multiply them by a prefactor. So C, it's something that goes from T star across T star to C, I guess. And so you plug in the weights, and that's the prefactor that you have to multiply with.
So the product becomes dependent on these weights, and it's really only a rescaling of the commutative tensor product that you obtain.
Yeah, it's like the quantum torus, but it's kind of compactified.
Mm-hmm.
Yeah.
But for all toric varieties, it's just somehow projectively, I would say that this is almost trivial, right? I mean, but it has this effect on. Mm-hmm. Okay. Thank you.
Other questions?
Can I ask another one?
Yes, go ahead.
Thank you, Francis, for your talk. Very thought-inspiring. I was wondering, so how in the last slides that you presented, the Santoli-Lito appeared. I was wondering how much your result is depending on that technology. So maybe can you maybe have a result of a different action of a different group acting on a Poisson manifold invariantly, and then produce a quantization, maybe an abelian group even, but.
I didn't quite understand the question. Like you mean if we have different examples?
Yeah, like in the same spirit that the one you have, right? Just replacing the torus action by a different group acting.
So I guess these are things that are work in progress. But the key thing is that the key thing really is that we're using this L though as kind of a way of selecting which of the leaves of the polarization. If this it's kind of interesting, if this L wasn't here, if we weren't using this L, then we would just be doing geometric quantization of this bigger space, and in that case we have these two different polarizations, the one given by the vertical and the one given by these other fibers, and in this case we see that it's not independent of polarization. It's only when you impose this intersection property, this kind of intersection constraint, that the result is independent. So I guess something like that would have to come in general, and that's something that's work in progress.
Yeah, that was like exactly what I meant. because here you know how the image of the moment map is going to be, but in general. Okay, thank you.
Many questions, but I think we have to finish now. We have a delay of 20 minutes. So thank you very much indeed for your talk. And go again.